Okay, there's two things I want to talk about. The first is the Archimedean property of the reals. Okay. The Archimedean property of the reals states that if we take steps of some certain size, we can get past every number on the real line as long as we take enough steps. So the step size has to be positive. So if x is bigger than 0, that's going to be the step size. And y is a real number, so that's the number that we want to get past. Then there exists an n in the natural numbers such that x times n is bigger than y. So I can eventually get past y as long as I take enough steps. So let me write down that English statement after this math statement. If we take positive sized steps, we can eventually get past any number on the number line. Okay, let's prove that. And this is going to be another proof using the least upper bound property. It's also a proof by contradiction. So we're going to assume something that we know to be false. We're going to get an absurd statement after we make that assumption, and therefore our assumption must have been false. We kind of know it's false to start with. That's why we're making that assumption, so that we can work with it and then get an absurd statement. Okay, so our absurd statement is assume x times n is less than y for every n in the natural numbers. That's kind of exactly what this statement is not, right? It's the negation of that there exists a number that gets past y. The negation is there's no number that gets past y. That means that every x times n is smaller than y. This is the statement that we want to be false. So let's let S be the set of x times n for n in n. By our assumption, y is an upper bound for this set. Okay. Since y is an upper bound, it has to have a least upper bound. We're going to say that least upper bound is alpha. So the least upper bound of S is equal to alpha. Okay. Since it's a least upper bound, if I take a small step backwards, there's going to be something in S that's bigger than alpha minus that small step. That small step we're going to take backwards is going to be x. It's not a least upper bound, it's the least upper bound. Alpha minus x is not an upper bound. Okay. Therefore, there is some x times n in S with x times n bigger than alpha minus x. Alpha minus x is not an upper bound because it's smaller than alpha, which is the smallest upper bound. There has to be something in the set that's bigger than x minus alpha minus x. Now I just have to add x to both sides and we get our contradiction. X times n plus 1 is bigger than alpha then, right? If I add x to both sides, I now have n plus 1 x's on the left. I just have alpha on the right. This means alpha is not an upper bound, which is our absurd statement. Alpha is the upper bound and it's not the upper bound. We had to have gone wrong someplace. The only place that we logically made an error could have been that assumption. The only place that there could be that error is that first assumption. So the statement x times n is less than y for all n is false, which proves the Archimedean property of the reals. Okay, this property is really useful because it just sort of says I can keep going as long as I take positive size steps. That's useful. It's sort of silly as a statement, but mathematically it's sort of a foundational statement that we need to prove before we can build upon it. Okay. The last thing I want to do in this video is I want to talk about rational numbers being dense. For something to be dense, there's a lot of it, right? In a little space. So the rational numbers being dense inside of the reals means there's a lot of them inside the reals. What does it mean to have a lot of numbers inside of some other numbers? Well, our mathematical statement is if x and y are real numbers with x less than y, then there exists p, a rational number, with x less than p less than y. So no matter how close together x and y are, as long as they're not equal, we can fit a rational number inside them. Means like there's a lot of rationals inside the reals. They're kind of everywhere. You can't sort of put a space between two numbers and not find rational numbers inside them. This statement is more than there's just one there, because I can sort of reuse the statement with, say, x and p the next time and find another rational between x and p. And then I can do it again, and I can do it again. And there's an infinite number of rational numbers between any two numbers, no matter how close together they are, as long as they're not equal. Okay. So let me write down the English statement, and then we'll prove this. between any two numbers there is a rational number. Okay. So let's prove this. And we're going to use the Archimedean property again. The Archimedean property we're going to use, it sort of goes like this. The space between them is going to be our step size. So x minus y, no, sorry, y minus x, that's bigger than 0, right? Since y is bigger than x. So by the Archimedean property, we can find n times y minus x bigger than 1. We can find an n that makes this statement true. So I'll say n such that n times y minus x is bigger than 1, and that leads to y minus x is bigger than 1 over n. Okay. So if I was going to look for a rational, a denominator of n seems like a good spot to look for a rational, because these two things are bigger than 1 over n apart. So on a number line, here's x, here's y past it. If I take steps of size 1 over n, even if I start like right here on x, 1 over n is not going to quite get me to y, right? So this, whatever this number is, if I take a step of 1 over n backwards, I'm probably outside there. But whatever this number is, this first number that gets past x with something over n, and this one is going to be something plus 1 over n, it's going to lie between x and y. This is the number we're looking for. Okay. So let's use the Archimedean property again to find that number. So by the Archimedean property, there exists m such that m times 1 over n is bigger than x, right? I can take steps of size 1 over n. If I take enough of them, I'll get past x. We'll take m of them, and let's say that this is the smallest such m. So that m minus 1 over x, or sorry, over n is less than or equal to x is less than m over n, right? I can find an m that does that using the Archimedean property. Now let's show that m over n is the p that we want. Okay, this is because, well, I already have the statement written down that x is less than m over n. And, well, let's go back and write down the statement that y minus x is bigger than 1 over n, right? Let's add x to both sides. Y is bigger than x plus 1 over n. And x is bigger than or equal to m minus 1 over n, so that this is bigger than or equal to m minus 1 over n plus 1 over n, which is equal to m over n. And now I have the inequality that y is bigger than m over n. Putting these together, we get x is less than m over n is less than y. And that's the statement we wanted to prove. Okay.